Hi, David Vizard here, and you are watching PowerTech 10. Give me a few minutes of your time and I'll give you the benefits of my 50 years of race winning experience. And that's not just at national level, that's international level. So what's our subject today? Well, it's going to be one that's going to affect most domestic built V8 engines, and that is predominantly lifters which are hydraulically adjusted. There's a lot of misconceptions going around about lifters and hydraulic ones in particular, so now's time to put you in the picture for real. I have to say, you're probably going to hear a lot of contradictions to some of the things that you'll see in this video. My answer to this is, I have tested so many cams that I'd probably be in the Guinness World Book of Records on the number of pulls I've done on camshaft testing. Let me give you some relevant numbers here. For about 3 years I was testing cams for Harvey Crane. Did about 8,000 meaningful tests or meaningful test pulls on the dyno on just small block Chevy cams. For Kent cams in England, I did on several engines about 11,000 pulls and designed them a range of best-selling cams. So I'm not coming from a journalistic point of view here where I ask somebody else. I'm coming here as somebody who is an accredited research engineer. That's me. You're getting this story with no middleman. So trust me, if there is a mistake, it's mine. But I'm more inclined to think that whoever contradicts this will be making the mistake. But anyway, that's open for conjecture, so let's get on with the story. First, let us look at why we have hydraulic lifters. The reason we've got hydraulic lifters is to quieten the engine down. Big V8 engines can make big V8 valve train noise with solid lifters. And Detroit was hell-bent on having the luxury aspect of owning a Detroit-built engine. That is, it had to be good on performance and run very quietly. So the hydraulic lifter came into being just because of that. Solid lifters, because of the lash in the valve train, tend to make quite a bit of a clatter. The hydraulic lifter has the intent of removing the clearances between the working components of a valve train. Now I want you to remember that bit because it's very important in what I'm about to say. Noise, however, wasn't the only criteria that Detroit was concerned with. The American public at large, or in general, were not too good at servicing their cars. The service intervals were often overrun by quite a bit. Also, if we're going back to the era when hydraulic lifters were introduced, the oils weren't so good as they are now. And that 3,000 mile oil change was a damn good idea if you wanted to keep that engine running. So durability of the valve train was also a factor. As performance enthusiasts, we need to look at our hydraulic valve trains in terms of not just noise, but reliability and performance. And that's just what we'll get onto now. Let's make our first move cutting the distinction between a solid cam and a hydraulic cam. What I've got here is a set of conventional solid lifters. They don't look much different to a hydraulic one. They're called solid because there is no motion of the plunger in the body. Also, they're easy to determine that they're solids because a good solid lifter will have a circlip in this groove in the top instead of just a cheapo wire grip, right? So when this takes up the lash, that valve train's opening right now, deflections or no. So it can be noisy, but it's a good performance item. Now let's have a look at a typical factory hydraulic cam, right? This might be too far away for you to see, but it's just got a round wire clip in it. And that's fine. They don't come out very often unless you've beaten the valve train to death by running into valve float or valve train control issues. Now, it doesn't take much to convert one of these factory hydraulic lifters into a performance lifter, but we'll go into detail on that later. Let me tell you a little story about hydraulic rollers, right? When I was doing a lot of testing for Crane, they decided to introduce hydraulic lifter cams. Now, at the time, Crane did not make the lifters. They simply acquired them from a well-known OE manufacturer. Well, here's the deal. These hydraulic rollers, now I need to emphasize that, rollers, the early ones, had a propensity for collapsing. The factories using them as the OE stuff, they weren't testing them at RPM that you and I as performance enthusiasts are likely to turn our motors to. But even so, at about 4,500 RPM, they could start to lose lift by virtue of the fact that the roller lifter was collapsing. Now, you might ask, does this happen to a flat tappet lifter? No. If we look at the geometries involved, a flat tappet lifter has very minimal side loading. All the loading is in the direction of the plunger. I say all of it. There's a small component due to friction on the flat face, but compared with other loads, it is very small. So we might as well say it's inconsequential. Now, with a hydraulic roller lifter, we get side load. If you look in my How to Build Horsepower book, you'll see there's a diagram and it shows a cam profile coming round and it puts a side load on the lifter which distorts the body. And under these conditions, the lifter leaks far more than you'd expect it to. What happens? The lifter collapses. Now, things have got better, but they didn't get better overnight. A few years ago, I was running with a friend of mine, a late model Stalker. And when we were on the dyno, one of the things I noticed was, and it was a sealed engine deal, one of the things I noticed when on the dyno was that the power seemed to drop off very quickly at about 5,600, and I suspected lifter collapse. So, since we couldn't get into the engine, we had to cure it from the outside. How do we do that? Well, I had this idea, and it came in the form of a simple phrase: long chain polymers. Right? So what happened here is, amongst my group of die-hard racers, one of them knew an oil scientist up in Canada. So we called this guy and had him brew us some various oils with different amounts of long chain polymers in. Now, a long chain polymer, it vastly reduces the amount of leakage you can have in a lifter. The downside is too many or too much of the long chain polymer stuff is going to cause the viscosity of the oil to increase. Result, viscosity induced power reduction becomes very noticeable at high RPM. So we had to find a happy medium between leakage in the lifters and viscous drag. Now here's an irony for you. I'm just going to backstep here. I called the manufacturer of the lifters, right? And it's not GM. They buy their lifters out. And I spoke to one of the engineers responsible for designing this. And I said, can you advise us anything we can do to prevent lifter collapse on your lifters? And he said to me, what lifter collapse? And I said, well, when you get to about 57, 5800, they start to collapse. Oh, well, we never go that high. So I said, you've never experienced on your Spintron or test data any lifter collapse? No. And I thought, there's a fine bunch of engineers for you. But I'm being critical here. Now, this was before the long chain polymer idea. So anyway, we finally, after testing a bunch of different mixes, we finally settled on an oil that had the right balance between viscous drag and lifters. And the amount of horsepower that we picked up over a well-known and very well-respected race oil was 14 horsepower. That is a lifter which is not collapsing. Let's go on with another story here, right? And you'll understand the severity of the situation with roller lifters, at least, when they were first introduced. And I'm dwelling on this now because roller lifters are such a popular type of lifter to go with, and hydraulic lifters are really ruling the roost here. So the first lifters that came out were so bad that rather than have a hydraulic roller valve train, I would opt to have a street roller type deal, which is a solid but quiet ramp street roller. And this is where I got my experience using some of Comp Cam's street rollers, and I was well pleased with how low the noise level was. Not quite a hydraulic intensity, but certainly close to it. Now, so how bad were the rollers, the hydraulic rollers? Well, here's the story. I just built a very stout big block, and I have this friend of mine who was an engine builder, and he built engines for off-road racing, and I believe he won the big off-road race they have in Baja, the Baja 500 and the 1000, at least once. So he's an experienced race engine builder. However, just because you're a race engine builder doesn't actually qualify you, or doesn't necessarily qualify you as an all-round engine builder, right? And so I said to him, well, here's the proposition he came to me with. He would do all the work on the engine. Any parts I could get that for him, for test purposes and publicity, that would be good. But if not, he would buy them. Now, the idea is that he would do all the engine building in my shop with this engine so that I could go on working on my engine whilst just over the other side of the shop he worked on his. So I was getting the work done on two engines to do two articles instead of one. Great. Twice the output of editorial material, but still only about 1.1 times the amount of work. Now, he insisted on having a hydraulic roller, and I said, no, you won't like it. He says, look, that's what I want. And I said, okay, I'll tell you what, I will call and see what I can do for cams. Well, I called Comp, and they were gracious enough to let me have a hydraulic roller for this guy's engine build, right? And just so that I had a backup when this cam failed, not because it's a bad design of profile, bad lifter, I could still get a story because I was going to put comps, solid street rollers. Right, now this guy chose a cam. He wanted about 280 degrees of duration. Right, the cam I picked, I believe, was 264 degrees of advertised duration at 15,000. So it was quite a bit shorter. Not as much as it sounds from there, because it takes the lash up before that 15. So the reality is it was about 8 degrees shorter. Well, we dynoed the engine on this guy's hydraulic cam, and I said, well, what do you think? And he said, yeah, it's okay. And I said, no, you're not really happy about it, are you? Well, no, I guess not. I'm just, right. So we swapped over his cam, which, by the way, I spec'd out. He just chose a hydraulic roller. And we put my solid roller, which I spec'd out. So how much difference do you think there'd be in horsepower and torque? I know you'll find this hard to believe, but it was a solid 105 foot-pounds and 120 horsepower. If you think you can afford to throw that away because you want a quiet valve train, then you can't really qualify as a performance enthusiast. Now, fortunately, we don't have to put up with that trash these days. Hydraulic rollers have become very effective. Thank goodness. Let's put a break on this storytelling for a moment and look at some of the details on flat tappet cams. Well, first off, flat tappet cams aren't flat. They've actually got about a 100-inch radius on the face of the lifter. And this, combined with about a thousandths taper across the profile, causes the lifter to spin in the bores. Now, if it doesn't spin, that is absolute surefire move toward lifter destruction, as well as cam in most cases. Now, the thought that these lifters actually rub one on the other at the speed the cam's going at is kind of misleading. Because the lifter rotates, the velocity between the surface of the cam and the lifter itself is a lot less than it would be if the lifter didn't rotate and the cam was in the middle. If you look at the profile, you'll see it's offset one side. Now, let's look at another aspect. Back in the early days, there was something that a lot of racers suffered with called lifter pump up. Now, you might think, well, that's obviously a lifter problem. Well, actually it isn't. This is one of the most misunderstood things there is. The fact of the matter is that the lifter is doing exactly what it should do, and that is take up excess lash in the valve train. So, if we go into valve bounce, or we lose control of the valve train because of spring surge and it opens up gaps, what happens is the lifter pumps itself up to take up that lash or that unwanted clearance. Well, the lifter doesn't know it's unwanted. Its job is to take up excess clearance, and it did just that. Now, some smart aleck in the cam business, and I know this gentleman well, came up with the notion that he was going to market anti-pump up lifters, which is exactly what he did. And do you know what an anti-pump up lifter does? It leaks down so fast that it can't pump the system up, or in most instances it can't. Well, that's not what we want. If your engine is experiencing what we call lifter pump up, it is not the lifter at fault, it is the spring that's being used. Springs go into surge, or they go into valve float, or they surge and then float. Now, spring surge, well, I'll tell you what we should do here. Go and watch my video on springs. It's going to go across the bottom of the screen here, the site for it, and you'll understand better what spring surge is and how to get rid of it. So that's the first thing. Now then, if your valve train is suffering from collapse, that's a lifter problem. You might have too much spring. Usually it's a combination of both spring, too much spring, and an inadequate lifter. The key here is to use no more valve spring than is necessary to get the job done. So let's take a quick look at that. I'm not going to go into too much detail here because I went into a lot of detail on the spring video, but here is roughly what I want to talk about. First off, you don't need to pay an arm and a leg for a spring. You just need to know what springs work and what don't. And when I say don't, there's a lot of springs out on the market which they'll work, but they're mediocre, right? You may pay more than you need to get that performance. Now, if you want a cheap upgrade on your Chevy, Ford, or Chrysler, Urson has a very good single spring, as do Pack. Again, it's in my spring video. But here's what I mean by buying the right spring for the job. Now this is a pretty good spring here. It's exactly the same specification in terms of stiffness, preload on the seat and over the nose load, as this one. This spring here weighs in at 145 grams. This spring here, which will do a better job, is only 132. This spring here is almost equal to running titanium lifters. This will perform as well with the steel retainer as this one does with titanium retainer. Now, you're better off with buying a spring like this. Again, for details, go to my spring video. It goes into a lot of detail there. Now, here's something that we can consider for our hydraulic valve trains. First off, let's look at spring rate. We don't need a spring any stiffer than about 300 to 330 pounds for a flat tappet hydraulic cam, and we don't really need anything stiffer than between 320 and 350 for a hydraulic roller. That's a spring spec that will turn some pretty decent RPM. Now, the up and coming spring for hydraulic roller camshafts is this Beehive Spring. There's a version made by several companies. The ones I use are made by Pack or Comp cams. Comp has a new one out of this under the same part number. It's magic. This here is a spring of the future. Note that it is conical. This is where we're going in the future. A lot of spring in terms of performance, but unfortunately still quite a bit of money. You want a big block Beehive Spring? This one from Comp will get the job done. Big blocks, by the way, with flat tappet cams can be a problem. It's a heavy valve train. It has a 1.7 lifter on it, so it puts even more load on that camshaft and lifter. So you need to be particularly careful about the spring you select. It's not just an expensive spring, it needs to be a spring that's efficient. That is, it gets the job done with the least poundage. What else can we talk about here? Well, here's something that I'm dying to tell you about. Let's talk about zinc.